Hi, my name is Ari Greenberg from BR+A Consulting Engineers. In the next 5 minutes, I'm going to tell you a few of the exciting things we're doing today with heat pumps. So to start off, I want to just kind of get a frame of reference here. A lot of people think of heat pumps as a device that creates heat in a building without the use of fossil fuels. I really want to challenge that notion today and think of heat pumps instead as not just a device that creates heat, but really a device that moves heat. So heat pumps, we differentiate in terms of the way they move that heat, where they take the heat from, their source, which is ground, water, or air, and where they move heat to, their sink, which are the two typical fluids we use to heat and cool buildings, water and air. So really common types of heat pumps you're already familiar with are probably ground source heat pumps or geothermal, and air source heat pumps, which include air to water heat pumps shown here, but also heat pumps that are really common like mini splits and BR+A. So ground source heat pumps or geothermal are really great. They're extremely efficient sources of heating, but they're also really expensive. And that's partially because it's really expensive to drill wells and also because it takes up a lot of space to drill all those wells for geothermal. So it's becoming more and more common in our work instead are air to water heat pumps. And that's because we can typically fit a lot more air to water heat pumps on a project and get much higher levels of electrification, much more fossil fuel reductions, even though there's a slight penalty in terms of efficiency compared to ground source heat pumps. So air to water heat pumps are really exciting innovation at the moment, and manufacturers are currently competing to create higher and higher water temperatures, do so at lower and lower ambient temperatures, and do all that with higher and higher efficiencies, higher COP. And that competition is spilling over also into domestic hot water heat pumps, such as these on screen. And what's really exciting is the use of CO2 as a natural refrigerant, prized for its ability to create hot water temperatures at low ambient. Speaking of high hot water temperatures, another exciting innovation we're working with today is doing high temperature hot water heat pumps and even heat pumps that can make steam. Typically, of not being able to convert a building fully to low temperature hot water, particularly important in the retrofit world, where we don't have the luxury of time to convert all of our systems to low temperature 120-degree hot water that works with conventional heat pumps. And instead, we're retrofitting systems with high lift centrifugals like you see on the top left, and even heat pumps, which is really exciting, that can make medium pressure steam without fossil fuels for process uses and other types of applications. So the last type of heat pump I want to go through real quickly is called exhaust source heat pumps. So the fundamental principle of an exhaust source heat pump is that if we have a building with a good envelope, really only the last remaining source of heating or requirement for heating is the ventilation system. So if we can neutralize the impact of the ventilation system by recovering as much heat as possible from the exhaust airstream and use that as a source of heat for the building, we've essentially wrapped our whole building in a really warm blanket, and all the heat that we need to keep that building running can come from the internal gains inside, can come from the people, can come from the lighting, and come from the equipment. So in its most simple form, an exhaust source heat pump looks like this. We can put a cooling coil, an exhaust air handler, we can put a heating coil in the supply air handler or in the building in a VAV box, and we connect those with a heat recovery chiller, which is a water-to-water heat pump. We cool the exhaust and we heat the supply, kind of a Robin Hood type scenario there. The next kind of level up from this is when we start to integrate heat pumps into our heat recovery system. So this is an example of KONVEKTA, which is a glycol energy recovery system, probably the most efficient one on the market available today. One of the issues that plagues glycol energy recovery systems is that if you cool the exhaust too much, if you extract too much energy from the exhaust airstream, you actually start to freeze any humidity in that exhaust airstream, and the exhaust coil will block up into a big block of ice. But if you purposely freeze that exhaust coil and then thaw it again and really control that freeze and thaw cycle, that's when you remove that limitation. So that's something that KONVEKTA is now doing, which is really exciting, to intentionally freeze those coils. And that opens up the potential for us to throw a heat pump chiller into the mix here. We can purposely cool the fluid going to the exhaust airstream even further. And the more we cool the exhaust, the more we heat the supply. So in this application, we're able to get 65 degrees off of our air handling units at 0 degrees ambient without using any fossil fuels to do that heating. So I liken this to it's analogous to having a turbocharger in the system. The last type of exhaust source heat pump I want to go over is when we use a enthalpy wheel in combination with the heat recovery chiller. So this is applicable to mixed air systems like we would see potentially in a hospital. So normally, if you have air coming into your mixed air in your air handler that's too warm, What's conventionally done is in the winter is you would actually open an economizer damper and purposely bring cool air into the system to cool down that air. That is an extremely stupid thing to do in the winter. We're purposely bringing cold air into our building. Instead, what we're going to do is we're going to use the enthalpy wheel, pre-treat the outside air coming to the system, and then we end up with mixed air that's too warm. We're actually going to cool it mechanically with the cooling coil, and then run that through a heat recovery chiller, and that heat in the air handler becomes the heat we can then use in the building. So the heat pump in this case is a really strong example of using a heat pump to move heat to where we need it in a building instead of just creating heat anew. So the last thing I just wanted to say is to recognize that in most of our projects, we're not putting all our eggs in one basket. We're typically combining one or two of these approaches, whether it's exhaust source and air source or ground source, in all of our fossil fuel free projects to get all the way to the finish line.